Hello. My name is Chris Baines, and I'm an engineer at the developer relations team at Google. And I'm here today to speak to you about coroutines, and specifically about using them on Android in your apps. So before we get started, these slides are already available at this link. So there's quite a few URLs in the slides, so don't be worried about trying to get them. You can get them later from here. So Android, like most other UI frameworks out there, has a UI thread. It's single-threaded, and it expects nearly all of its UI updates to be done on that thread. So things include stuff like view inflation. You can do stuff off-thread. We actually provide something called async layout inflator, but it has sort of certain downsides to it, and it doesn't work in all cases. Stuff like measure and layout. Now, the bulk of your app, when it's actually on screen, is doing measure and layout. So if you change some text on display, it has to go for a whole pass. Drawing, a lot of drawing is still done on the main thread, although some of it is done off-thread now. So we have things like render thread for certain animations, and many, many more things. So all of your app code, at least the entry points, are mainly done on the Android main thread. And so when we think about devices these days, the refresh rate on most devices in your pocket will be 60 Hertz. And that gives you 16 milliseconds, or near enough, to actually make sure you update the UI and so it doesn't jank. But more and more devices these days, that refresh rate is getting higher and higher. So on a 90 Hertz device, you've actually only got 12 milliseconds to do the same amount of work. And again, 120 Hertz. The Razer phone was released earlier last year, this year even, and that is 120 Hertz. That gives you 8 milliseconds to do the exact same amount of work, but obviously in half the time. Now, if you look at systrace, you'll find that most of the things which take the amount of time, it tends to be app code, or at least stuff that your app calls, like layout inflation, layout, measure, all that kind of stuff. So how can we fix it? Well, I think you should async layout all the things. Most phones in your pockets will have 4+ cores, so we should use them. Get off that main thread as much as possible so that anything that doesn't need to be on it shouldn't be on it. Now, this talk isn't about trying to hit 8 millisecond boundaries, but it gives you an idea of the kind of problems that we as app developers face that we can actually fix with tools. So how do we do that? So in the past, we've given you a multitude of ways to do async. AsyncTask, back in Cupcake, came out. It's like a simple abstraction over threads. Unfortunately, it has all the issues we all know about, especially regarding rotation. Then we have Executors, which AsyncTask used to sort of be a level above. Now, threads themselves, when you create a new thread, it takes about a megabyte of RAM, or similar anyway. And so threads are heavy to create, so we should reuse them, and that's exactly what Executors do. Unfortunately, the actual API to run stuff is pretty basic. You run, and that's what you get. Loaders were added to fragments about 3 or 4 years ago, and they're a nice way to load data into your UI. Now, it was a nice start, but it's now deprecated. And the reason why is because it only really supported content providers and content URIs, and most developers don't use those, and we know that. Futures. So unless you're min SDK24, you can't use Completable future, and unless you want to import all of Guava, you can't use its stuff. So again, not really what we want to use. Libraries. And so I remember the days when we had stuff like RoboSpice, like, I don't know, 6, 7 years ago. And then we actually shipped Volley, and we actually gave you the source, but we didn't actually give you a jar. But then the community has actually rallied around themselves and created things like RxJava to actually do this stuff. And they're great. We're not trying to advocate against using them. It's just they're alternatives. So hopefully, if you're in this talk, you want to know more about coroutines. So I'm not going to go too much into that. So why actually use them? So when I was thinking about this question, when I was writing these slides, I was thinking, what does your typical mobile application do? And for the most part, they're CRUD apps. And I don't mean the American slang. I mean the fact they create, they read, they update, and they delete. It's all about data on screen, or locally stored. And then they might do some syncing. So they might sync to some kind of web service and then back down. So they're pretty simple apps, really, when you think about it. There's not, in your typical app, there's not really massively computationally complex. It tends to be tricky to get the stuff right rather than it being super computational. And of course, there's a lot of stuff in Android that gets in the way. It makes your jobs harder. So why coroutines? Well, I think they're great for UI tasks. And that's because they scale really well on limited hardware. We were saying earlier, a thread takes about a megabyte of RAM. Your typical coroutine is probably in the tens of kilobytes, so it's a lot less. And the other thing that I think is better is that they have a much easier development model. So instead of having to write something like an Rx chain, which is, if someone doesn't know Rx and they're coming in to look at your code source, it's kind of hard to read. So writing imperative, kind of sequential code, stuff we've been doing since anyone learned Java, is much easier to read. And so this is the app I've been playing around with for the past 12 months. It's been my playground for a lot of stuff. When I first started writing this app, it was completely RxJava, and I've kind of moved over the past 6 months to using Coroutines. And so it's roughly about half and half now in the way it works. And so a lot of the examples I use in the rest of this presentation is taken from here. One thing I'd like to note in this presentation is that this isn't an official Google endorsement for Coroutines or anything like that. This has been my experiment and what some of the sort of things I've come out of it with. And so I feel like Coroutines is still obviously a very young technology. And so we all need to come together as a community to actually work out what's the best practice. And anyone who says that they know the best practice other than Roman is probably lying. So one of the things I was looking at with Coroutines is actual APK size. So that's a thing Android developers have to worry about a lot. And so in my app, I use 3 libraries: Core, which contains the majority of what you're going to need in Coroutines; Android, which contains the Android main dispatcher; and then Rx2, which is a really nice library where you can kind of interrupt between RxJava and Coroutines. So when you actually look at the jar size, if you just download them off Main Central, it's about 774 kilobytes, which is actually quite large. I was surprised by that. But when you actually sort of drag it into your APK and you look at it, it actually comes down to about 500 kilobytes, and that's because it's packed in. So it's actually not too bad. But as soon as you start turning on minify, so this is minify without optimization, so it's just tree shaking, basically, that comes down really nicely down to 113 kilobytes. And in my app, I'm actually using quite a large proportion of the API. So if you're not using that much of Coroutines, that will come down even further. And if you turn on optimization, it comes down even further to less than 100K. So hopefully you can see that actually including it in your app isn't really a cost in terms of APK size anyway. One thing to note about using ProGuard or R8 with this is that you need to include this rule. This has been just taken from the GitHub, Coroutines GitHub repository. It probably is going to be updated over the day, but yeah. So hopefully by now you're thinking about actually using Coroutines in your app. So let's now talk about how you actually write them and actually use them. So here's a suspending function from the app. It's actually from the data repository, like the data layer within the app. And it's given a show ID, and it updates the show. It's pretty simple, really. The first thing it does is that it gets it from the local store, so the local database. Then it will get it from a remote source, the first one, and then from a second remote source, because it does like a merge. And then finally, it will merge all the results together and then save it to the database again. So pretty simple method, really. But if you look at those 3 tasks, none of the 3 tasks have dependencies on each other. They could all be done concurrently. So why don't we do that? And Coroutines makes it really easy. We just wrap each of them in an async block, and we sort of keep hold of it deferred, go for the second, go for the third, and then finally we can just await the result of each. And now all the 3 of those tasks are being run concurrently, and it takes less time. So that's just a small example of how Coroutines can actually help you. So how do we actually use them on Android? Well, here's the simplest example I could come up with, and it's a very simple view model. The first thing at the top are just actually being able to get access to the show repository. We don't really care about this at this point. And now, in most of my view models, I have an init block, and in there, I do a refresh every time. Because it feels kind of right that every time you create a view model, so each time it's coming to screen, we actually do a refresh, because the user always wants updated information. And in that refresh method, we will launch a coroutine, and that will just literally call our update show method. Pretty simple, really. But can anyone see the issue here? What happens if the view model goes away before that launch is actually finished? We need a way to actually cancel it. And that's where jobs come in. Now, what actually happens when you call launch is that it will return a job. And that job allows you to then cancel it. So we actually have a way to actually call back to that coroutine and cancel it while it's being run. Obviously, we wouldn't do it here because we wouldn't just launch something and then straight away cancel it. It's just an example to show you that the method is this. Really, we want to do it in whenever the view model is sort of destroyed. And that is in the onClear method. Oh, no. So what we do here is that we would keep a reference to the job. So in the top property, we'd have update show job, and then we'd update it. So every time we call lunch, we'd keep reference to the job, and then finally, in onCleared, we'd just call cancel. But the problem with that is that using the pattern is kind of a pain, because more than likely, you're going to have more than one launch happening, or async, or whatever it is. So you're not just going to have one thing run at a time. You might have 3 or 4 or 5. So if we have 2, we then have to keep track of 2 jobs. If we have 3, we have to keep track of 3 jobs. It gets a bit unwieldy and a bit too much code to actually maintain. Now, RxJava goes kind of a different route to what Coroutines does. RxJava gives you composite drawable, so you have a collection of things. So instead of having those 3 properties at the top, you'd give it a collection. You'd give it an item to a collection. Coroutines goes a different way, in that coroutines can have a parent and child relationship. And that allows us to track when coroutines are being run and finally cancel them if needed. And access express via jobs within a context. It's a critical class in the coroutines library as it represents sort of a bunch of work to track. So if we go back to our view model, how do we make use of this actual parental relationship? What is this? So first thing we're going to do is create a job. And that is created whenever the view model is created, because we want it to last the same lifetime as the view model. And this will be the thing that we actually set as the parent of the coroutines. Then in the launch, we'll actually give it the job as the parent of the launch. Once we pass that to the value, the job becomes the parent. And finally, on cleared, we've actually canceled the job. What that means is that that launch of coroutine is actually scoped to the lifetime of the view model. One thing to note here is that as soon as that job is canceled, you can no longer use that job again. It's terminal, it's dead. That brings us quite closely onto the subject of scopes and scoping coroutines to kind of a lifetime of something. The problem with the example I just gave is that you have to be very explicit over actually the parent. And it's very easy to forget to actually pass those parents down. So if we go for an example, here. So here we have our launch and the inner kind of method within it, just like in line. And you can see that that outer coroutine is actually running at this point. But we're at the yellow arrow, so we haven't actually entered this method yet. So we'll go past the first async, and we've suddenly got an inner coroutine running. And then we'll do the second, and that's also another coroutine. And these are new coroutines which are running. At this point, we'll keep going, and then we'll hit the first await. Now, at this point, that outer coroutine is suspended, waiting for the result of the first coroutine to actually finish. But during this time, the view model is gone. It gets destroyed for whatever reason. The screen goes off screen, which means that the job is canceled. Remember, we had that job, and we canceled it. But hopefully you can see that those 2 inner coroutines are still running because they haven't been canceled. And the reason for that is because there is no parent set. So we have the parent on the outer coroutine, but it doesn't actually automatically populate down to the inner ones. Now, all the code I've just been talking about for the past 10 minutes is actually deprecated. The reason I've spoken about it is that even the stuff that's in 26 and above uses this stuff internally. So it's important to know how it kind of works. And also, if you have legacy code, it's important to know why you want to move. So the new hotness is coroutine scope, and it's a new interface in version 0.26. So that was, 3 weeks ago? Which allows objects to provide a scope for coroutines. So the perfect example of this is like activities and fragments and services. Because they have a lifecycle themselves, we want the coroutine that's get launched to have the same lifecycle. Now, async and launch actually become instant methods on top of your scope. Well, not quite instant methods, they're default methods in the interface. But it goes from launching and building a coroutine just globally to instead, mentally anyway, you running the coroutine on X. So I'm going to launch my coroutine on my activity, which means, I don't know, it just makes it easier in my mind that you're scoping something to the lifetime or something. And you also get to provide a default context. And that allows us to actually slip in that job object, and so it comes all the way down. So if we go back to our view model, let's convert it to a coroutine scope. So we'll implement the interface, and then we have to give it we have to implement the property we call coroutine context. And that's that base context. And that's the thing we want to be the default for all the for launch and asyncs. Here I'm using the job that we created and also a dispatcher. I like to use dispatcher.main which is the Android main thread, as the default dispatcher, because I like to be explicit. Well, I think it's better to be explicit about going off thread rather than being explicit about going on thread. We'll talk about dispatchers later anyway. And then if we go down to our refresh and our launch, we can get rid of that parent because it no longer exists. And that's it, really. If you actually look at the method, semantically, this is kind of what it does instead. It's like this.launch, and it kind of points to the context that we have up there. So it's not exactly what happens, but semantically in my mind, that's pretty much what happens. There's more layering involved, but it's what. It's quite easy to abstract all the code I just mentioned into a nice little base class. It's pretty simple. There's not much to do. You can do the same thing for activity and fragment. You just change, obviously, the base class. So if we go back to our example, we also have to modify the suspending functions. Because as we mentioned, launch and async are now instant methods on a scope. And because we don't have a scope in this method, we need to get one. Luckily, there is a nice utility method called Coroutine scope, and that will create a new scope for us based on the one we're currently running, which basically means that we get access to async and launch and all that all over again. And once we use that, our async builds are actually scoped to the outer coroutine. So if we go for the example, again, we're running our outer coroutine, and we're at the top still. If we go past the first one, async's running, then the second, async's running. But these are now more child coroutines. They have that parental relationship is actually there. And again, we're going to wait for the await, at which point the outer coroutine is suspended. Again, the view model goes away, so we get canceled. But you can see that those inner coroutines have also been paused, or canceled, actually. You can see that the children are canceled, too. So hopefully you can see some of the benefits you get from the scoping and like the implicit functionality that we get now in the new versions of the coroutines library. But what if you're not using view models? Like we know at least some of you aren't using view models, or majority of you may not be. Now, as I mentioned earlier, you can also create a base class for fragment. Again, it's very, very similar to the view model, just different base class. But also, as part of the Android architecture components, which we released 18 months ago, we have now lifecycles. So we allow you to observe lifecycles, which tends to be much easier. So you no longer have to use those base classes. So here's a very small example. You create an observer, and you can implement any of the methods. There's 7 methods: create, start, stop, pause, blah, blah, blah. Here we're just using create and destroy. And then once you actually want to use them, you just get lifecycle, add observer. That's just a small context for how you use them. So if we actually want to create a lifecycle coroutine scope, let's build one. So we'll create the class, it's a skeleton class. And the only thing we really care about, as before, is on destroy, because we want to know when to cancel that job. So we'll create a job in the instance, and then we'll cancel it. There we go. Pretty simple again. And again, implement the interface, and then create a context. So this code's repeated many, many times, you can see. It's because this is pretty much the basis of what you have to do. And to actually use this is like this. So you create an instance of that class. We're going to use a fragment here, but it could be anything really that exposes the lifecycle. You add the observer, and then to actually launch something in the coroutine, you have to call scope. And then the actual launch is scoped to the lifecycle of the fragment. Now, if you're using, I don't know, a lifecycle of service, it'll be the same thing. Lifecycle acts as like a really nice intermediary, so you can decouple a lot of the code. Louis actually wrote a really nice implementation of this. I mean, the implementation we just went through is pretty simple, but Louis' one is actually much more complex, and you can actually do a lot more magic in it. So I'd really go and look at it if you need to use this stuff. So we talked a lot about canceling jobs and coroutines in general, but we should also talk a little bit about how it works. So cancellation requires cooperation. So it's kind of a bit like thread interrupts in a way, but it's a bit more less. And specifically, you need to check in your code whether you have been canceled. Or specifically, you need to check if you've been active. That's what the API is active. So there's 2 ways to cooperate. The first is simply by calling a suspending function. Most of the suspending functions in the library do this kind of code. It might not be the exact same, but it does something similar. Where like it will get the job, it will check if it's active. If it's not, it will throw a cancellation exception, and that's how the cancellation is bubbled up. Yield's a good example of how to do this, but await, delay, there's a few others as well you can do it too. So as long as you're calling these, you're already pretty much cancellation aware. Alternatively, if you're not calling any suspending functions, you can actually check the property yourself. So here's a very small example where we're iterating through some files, and then for each file, we are checking whether active before we actually do some chunk of work. That leads us nicely onto exceptions. We just spoke about exceptions, and a few things that have caught me out over the past 6 months or so. And they may catch you out, they may not. I don't know. The first one is that launch kind of rethrows exceptions. And so it's kind of similar to a thread in that if there's an exception that happens in your launch, it will get sent to the default exception handler. So in this example, we'll go back to our update show, and we're going to throw an exception at the bottom. Now, on Android, what that means is that it's treated like an uncaught exception, and then your app will crash, basically. The other one that caught me out a few times is that async doesn't actually throw until you call await. It will hold on to the exception, basically. So back to our example. In this time, we're going to throw the exception in the first async block. Now here, obviously just said, it's not actually thrown until the await. The thing that caught me out here, actually, is that I was accidentally using async instead of a launch. So I was actually using async as like a fire and forget type thing, which basically means that async will then swallow the exception because I was never calling await. So it's just something to sort of be aware of. And the way you actually handle this stuff is standard try-catch. It's nothing particularly exciting. So we've just talked quite a lot about coroutines now and how you actually write them. But it's important to know how they actually run on your device, and that's where dispatchers come in. So launch and its async and all those builders have a context, and the default one uses dispatchers.default. So what is an actual dispatcher? Well, it's the thing which runs and schedules your coroutines. It's the actual magic behind coroutines a lot of the time. The default dispatcher, which is called dispatchers.default, actually equals internally something called default scheduler. That is new in, well, I think it was v25, but it's only become the default in v0.30. But it uses CPU count threads. And so whatever the amount of CPUs you have in your device, that's how many, well, not threads, parallelism that schedule can use, with a minimum of 2. So you'll always have at least 2. As part of 0.25, a new dispatcher was added called I/O, and that's specifically designed for blocking I/O tasks. So this is the one which Android developers really should be caring about, because a lot of the time you're going to be doing network, disk, all that kind of stuff. So this is the one where you should be using quite a lot. And instead of using CPU count, it has a minimum parallelism of 64. So you can have up to 64 things running at a time. Which you think sounds like a lot, but when you think things like loading images on a grid or, I don't know, whatever it is, that's a good number. The really great thing about the I/O dispatcher and default scheduler is that I/O uses default scheduler internally. So they actually share threads. So if you look at this example, here we are launching an async using the default dispatcher, and we'll immediately switch to the I/O dispatcher and then load an image. We're doing some disk reading. After that, we're going to do some processing of some kind, but we rely on doing that on the default dispatcher. Now, because they kind of share threads, it may not actually switch your threads around. So there's no thread context switch, which take time anyway. So because they share threads, you may not actually switch threads, and then you save time. So reactivity. How many blog posts can be summarized as this slide, lately anyway? And I myself have been one of those people. I'm going to make the premise that most developers, at least, get into using RxJava just for the easy threading model. I'm not saying everyone, but I'll say a lot of people use it just because they want to use schedule on or observe on to easily switch threads. And I'd say that a lot of them end up mainly using single, maybe, and completable, like just the single value types. Now, they only exist in RxJava, RxScala, and RxGroovy. So when I was thinking about this, is that maybe that's more a reflection of sort of the platform APIs that they run on, because they're all pretty similar, rather than the fact that they need to live in Rx. So I was thinking that coroutines can actually quite easily replace single, maybe, and completable. But actually, you actually get all the benefits of coroutines, like the imperative style. So if we go for an example, here's a retrofit example, which everyone likes to use. And we're going to have an endpoint called trending shows, and that returns a single of a list. And the way you'd actually consume that on RxJava is that you'd do schedule on to switch onto some kind of scheduler, and then you'd subscribe. This is standard Rx. Now, you can actually consume that single quite nicely in actually coroutines. So there's a lot of nice extension functions within the Rx2 extension library on coroutines, which allow you to kind of easily convert them. So there's a nice one called await, which is on single and completable and maybe. And so you can just actually consume them completely in coroutines, which is really nice when you're actually already using RxJava and you want to kind of switch over to coroutines. So you can do that kind of step-by-step gradual migration, if you want to, using these extension functions. Now, wouldn't it be nice, instead of actually return a single, that we could just make that retrofit interface just a suspending function? Now, this is actually coming soon to retrofit. I was talking to Jake earlier, and he said they're just waiting for 1.3 to come out, and then they're going to release it. So that's going to be really cool. Which means that our calling code literally comes from that down to that. We remove the await because we no longer need it. It's just a standard suspending function, and it looks great. And that brings on to channels. Now, the one thing to be aware about channels is that they're still experimental, and they kind of feel like they need a bit more. So I feel like they're not really a replacement for RxJava publishers. The closest thing they probably are is the Flowable, because they have back pressure support. But they feel close to me like a kind of suspending dequeue, which I guess that's what they're actually called in the docs. But they still kind of describe an async stream of things. Channels call these elements. RxJava calls them items. It's just semantics. Yeah. So if we go for a quick example of how you can actually send and consume them. So we'll create a channel. And this channel is going to be a bitmap. Our first one is our sending side. So this, we're going to launch a coroutine, and that is going to sort of iterate through a list of files and then just load them. It's going to read them from disk and then send them to the channel. It's pretty simple, really. Finally, once we've consumed all of those files, we need to actually close the channel. We need to actually explicitly say channel.close. Once that's done, we can actually launch another coroutine to actually consume them. Now, in here, it's in the same file as such, but they could be at two ends of your app. It doesn't have to be the same thing. But here we're going to launch it, and then we're going to use the consume each method. And what that does is it opens a subscription onto the channel, and then consumes each item until it's been closed. At this point, we can do other stuff like process it. So that's a super trivial example of a channel. Now, we're comparing channels to RxJava. They kind of have similar things. Like broadcast channels are very similar to a subject. Conflated broadcast channel is a special version, which is also kind of similar to a behavior subject. So if you're using them, you can kind of swap over. Some small differences. Channels actually support null values, whereas RxJava, if you send it a null value, it will crash. And channels only support hot streams. So that's a bit of a fundamental difference. In terms of operators, so RxJava is known for its many, many operators. Channels has roughly 73 from my count yesterday, built-in operators, and a lot of them are kind of collection-type methods. If you compare that to RxJava, it has many, about 230 from my count yesterday. Now, a lot of them are not really applicable to Kotlin, because some of them are like function zero, where you don't really need them when you have a Lambda. And it also comes with a downside when you have so many operators, I find. In that I found when I was learning RxJava that the more operators there are, that it's just so unwieldy trying to learn it all. And so it actually does come with a complexity which is hard for beginners to learn. One of the things that I like with coroutines anyway is that these operators are actually nicer to write. So if you were to write an RxJava operator, it's actually quite a lot of work. But in coroutines, it's a lot easier. So here we're going to write an extension function on publisher, which implements a map. Obviously, publisher already has a map. Well, at least Flowable does. So if we actually implement it in coroutines, the important bit here is that literally you just give it a mapper, which is a lambda, and then it consumes each, maps it, and then sends it straight back. So it's pretty simple, really. So my final section in this presentation is about actually converting Android APIs to using coroutines. So there's two examples I have, two examples which I'm sure a lot of apps actually use. The first is actually getting the last known location. In this example, we're going to use the Fuse Location Provider Client API, which is a very bad name, but it's in Google Play Services. And it's actually quite a nice API in that it kind of merges together all of the different location providers for you into a nice single result. So GPS, Wi-Fi, network, Bluetooth, all those, it merges together and handles it all nicely. Because it's Play Services, it actually returns what they call a task, which is, for all intents and purposes, a future. So the API we're going to use is called client.getLastLocation. And that returns a task, which as a result type of a location. And here's how you would use it normally without coroutines. You just add a non-complete listener, and then as soon as the actual task is completed, you will get the result back. So if you think what we're actually doing here, we are converting a callback API into a suspending function. That's pretty much what we want. And luckily, the coroutines library gives us a really nice way of doing that called suspend coroutine. And what suspend coroutine does is that you give it a lambda, and it expects in that lambda that you will set up your callback and actually sort of trigger the task, and so it actually starts working. At that point, it will immediately suspend, waiting for that callback to come. You're given a continuation object, and that is how you later tell the coroutine to start running again with the result. That's how you pass the result. So if you actually start writing our skeleton method, we're going to have a suspending function called getLastLocation, and that returns a location object, like an actual straight-up location. We're going to use suspend coroutine straight away, and then we have that continuation object passed to us. At this point, we can actually call the Google Play Services API. The important thing here is that we call back to that continuation so that the coroutine actually finishes and gets a result. And that is done here with the continuation.resume. So we actually just get the result and just pass it back via the resume method. Now, since Play Services is a task, so it's basically a future, it doesn't just handle the success case, it handles the failure case too. So that means that we can bubble up any exceptions that happen up to the coroutine too. And we do that via the resume with exception method instead. It doesn't have to be for any sort of kind of callback. If you have it just run to exception when you're doing this code, you can also do it with resume with exception too. So that's the kind of more simple example, which is actually just getting one callback, getting one value back, and then having a suspending function. But most of the time, you might actually want to observe location updates too. You think like maps or, I don't know, a navigation app. You want to actually observe the location so that you're always updated when the location changes. And that is kind of like a multi-value callback. Again, we're going to be using Fuse Location Provider Client, a different API this time called Request Location Updates. So it's slightly different to the first API in that you request, and then you'll give it a callback. And that's the callback. It will tell you if any locations change. So you look at the API, there's 3 parameters. The first one is called a location request, and that is how you define sort of location parameters. So I don't know, you want to only be notified when the location changes by 10 meters or something. Second, you have the callback, which is what will be called back on. And then thirdly, we have the looper, and that is the looper, or the thread in Android, well, kind of thread in Android terms, that your callback will be actually invoked on. And as we mentioned earlier, you call the API to start location updates, but you also need to tell it to stop, and that is done via remove location updates, so that it can like free up GPS and you're not just killing the user's battery. So let's build our function, our suspending, well, not suspending function, our coroutine function. So we'll create a function called observe location, and we still want to pass in the location request, because we still want the caller to be able to define that stuff. But this time, we'll return a receive channel, an actual channel of locations. So let's build our function. So we got this, and then we will create a channel straight away. That's the thing that's going to be returned, and so that the caller can actually observe it. Now we're going to create our callback. This is the play services stuff. We create it as an instance because of the way the play services API works, in that you need to give it the original callback to stop it all at the end. So we need to sort of save it as a value. The important thing here is that once we have a value, and once the callback is invoked, we just send it straight to the channel, and we will use sendBlock in here. The reason we use sendBlock in is that because we're running the coroutine, we don't really care what thread it's been running. We're just happy to run whatever coroutine thread we're in. So at this point, we actually need to start kicking off the location updates. So we'll just call request location updates with our request, our callback. And because, as I said, we're happy with whatever thread we're running on, we'll just use looper.myLooper, which is a utility method in Android, which is just basically whatever looper is currently in my thread. One of the neat things you can do is you can actually add a listener onto channels, which are invoked whenever they're closed. What this allows us to do is actually neatly, well, quite neatly anyway, hook into the channel, and so that we can automatically tell play services to stop doing location updates automatically. And that's exactly what we do. And we invoke and close, and we just call remove location updates. So if we actually look at how to use this kind of method that we just created, so we'll store the location channel. It's probably a nicer way of doing this, but it's what I came up with this morning. And then on start, we'll actually start trying to observe that location. So in this request, we're just doing a minimum displacement of 100 meters, whatever it is. But the important thing here is that we call observe location, and then we store that channel. At this point, we can actually start using the channel. So we'll launch a coroutine, and then we'll call consume each, which is the method we sort of showed earlier. And then that will be invoked repeatedly when an item is emitted, RxJava term, but sent into the channel. And then on stop, because we need to tell the channel to actually close, we'll call cancel. And because we have that invoke on close listener that we spoke about earlier, it will automatically bubble up to the play services API and tell it to stop observing locations. All right, so that's it. If you want some information on what's next, we actually launched a code lab 2 days ago, which is all about using coroutines in your app. So check that out. Also, read the manual. The guides are really, really good. They're very use case driven, and so they're all about a use case and then the idiomatic way in coroutines to do it. And so make sure you read them all. And thirdly, there are 3 great talks happening tomorrow all about coroutines. Make sure you attend them. That is me. Thank you very much, everyone.